We're looking through notes for 8.8 improper integrals. The definition of a definite integral, integral of f of x from a to b, requires that the interval on the closed interval from a to b to be finite. Furthermore, the fundamental theorem of calculus requires that our function is continuous on that closed interval from a to b, right? No breaks. In this section, however, we're going to learn a way to evaluate integrals that do not meet these requirements. We'll see problems where one or both of the limits of integration are infinity, and integrate functions that have indefinite discontinuities in the interval from a to b. So we could have infinity on the boundaries, or we could have an internal discontinuity between a and b. So intervals that possess either property are called improper integrals. A function is said to have infinite discontinuity at c if the limit as x approaches c of f of x equals infinity, or limit as x approaches c of f of x equals negative infinity. So let's look at example 1 here. It says evaluate by using our calculator. This is here is a portion of the graph of 1 over x. It's the curve that's going to go down and get closer and closer towards the x-axis here. So we're just doing some approximations here. So the integral from 1 to 100, so imagine if this graph continued, this graph get closer and closer towards the x-axis, but there's always going to be that gap, so we're going to be able to evaluate the area from, if we evaluate using the calculator, using the FN integral feature, integral of 1 over x from 1 to 100 will give us 4.605, and if we extend that area out to 1,000, from 1 to 1,000, it'll be 6.908. 1 to a million will be 13.816. So we see that even though this graph is closing in on the x-axis, it's not closing in fast enough to cause this function to get closer and closer towards a sum. So we see that the sum is still increasing. So based on the values above, our guess or of what's happening if we were to go from 1 to infinity is that this 1 over x is going to go to infinity, that this series or this sum will not converge at a particular sum, but it will be divergent. So this brings us to our first rule here. If a is greater than 0, then the integral from a to b of 1 over x to the p is convergent if p is greater than 1 and divergent if p is less than or equal to 1. So these are called p-series integrals. So if a is equal to 1 as p is greater than 1, then the integral of 1 over x to the p from 1 to infinity will converge to this particular sum, 1 over p minus 1. So the idea is that even though 1 over x is getting closer and closer towards the x-axis, it's not closing in on the x-axis fast enough to allow for the area to converge. But if we have any power that's greater than 1, let's say 2 for instance, then 1 over x squared will converge at a fast enough rate towards the x-axis. It will not close off, but it will close in on the x-axis fast enough to allow the series to converge, or the sum to converge from 1 to infinity. So if we see this form, then we just have to look at that p-value. If that p-value is greater than 1 or greater than 1, then we know that the series will converge. So 1 over x to the 2/3, we see that this is in the form of a p-series. 2/3 is less than 1, so the 1 over x to the 2/3, the graph is not going to close in fast enough on the x-axis, so the sum will be infinity if we're going from 1 to infinity. 1.1, notice that 1.1 is greater than 1, so the series will converge, and the sum that it converges to is 1 over p minus 1, so p is 1.1, so 1.1 minus 1 is 0.1, 1 over 0.1 is 10, so there's our sum. X to the negative 7, if we rewrite this, put it in the denominator, it's x to the 7th in the denominator. This 7 is greater than 1, so the sum will converge, and it converges to this value, 1 over 7 minus 1, which is 1/6. 3 times x to the negative 3/2, so negative 3/2, we can bring that down to the bottom, and we can evaluate the limit. We can notice that this is p-series, that converges since 3 halves is greater than 1. So we do 3 halves minus 1, which is 0.5. So 3 over 0.5 is going to be 6. Integrals, such as integral from 0 to infinity, or negative infinity to a to infinity, negative infinity to a, and negative infinity to positive infinity, are called improper integrals. So improper integrals, a couple of points here. They have infinite interval of integration. They have discontinuity on the interior of interval of integration, or they have both. So all these are possibilities of improper integrals. So let's look at number 1 here. The integral from 1 to infinity of e to the negative x. So if we have infinity here, we can use a variable. Usually we use the b to represent that infinity. So we're going to rewrite this to help evaluate that b value, that infinity value, a little better. We're going to represent that as limit as b approaches infinity from 1 to b of e to the negative x. All right, so now we're going to approach this like we would a definite integral problem. So we're going to evaluate the integrand here. So e to the negative x, we can go through u substitution. This will give us negative e to the negative e to the u, and the integral for e to the u is just going to be e to the u, and we have to include that negative. And then, so here's our antiderivative. Now we can plug in our upper and lower bounds. So plug b in first. So we get negative 1 over e to the b minus a negative e to the negative 1, which is 1 over e. And now we can now we have it in the form that we can now evaluate the limit as b approaches infinity. So as b approaches infinity, we know that this expression will go to 0. And then this is a constant, so 1 over e plus 0 will be 1 over e. So we know that this series will converge to 1 over e, or the sum will converge to a value 1 over e. Okay. Let's look at part b here. Negative infinity to 0 of e to the x over 4. We can go through, let b represent negative infinity. Go through antiderivative here. If we go through u substitution, u value is x over 4, which will, if we go through substitution, it'll produce to be 4 over 1. So the integral of e to the u is just e to the u, and then we have to also account for the coefficient that comes from u substitution. Upper bound first, so plug 0 in for the antiderivative, and then plug b in to antiderivative. Now we can evaluate as b approaches negative infinity. So nothing to plug in here. This will just give us 4. B infinity gets plugged in for the b here, which will go to, but it's negative infinity. So basically e to the negative infinity, which is 1 over e to infinity, which is going to be 1. So this will give us 4 minus 1 over e to the infinity will produce 0. So 4 times 0 is 0. So 4 minus 0 is 4. Part C, notice that this is a p-series integral. So we see that this p-value is 1, x to the first power. So therefore, we know this series will diverge to infinity. Okay, let's look at a couple from the back page here. Example 4. We have the integral from 1 to infinity of 1 minus x times e to the negative x. Notice that we have two pairings of different types of functions. We have polynomial here, and then we also have polynomial or algebraic, and we have exponential. So maybe the best way of working with these two types of functions is to go through integration by parts. So we let the u value be 1 minus x, and then we just find the derivative until we get to 0. And then on the right side, we keep finding the integral until we reach the same number of times that we found the derivative. Okay, and then we multiply the diagonals. So here we have the antiderivative. We can now evaluate the upper and lower bounds, plug in b into the upper bound, as the upper bound plugged into the expression, followed by 1. Okay. So then we're left with b over e to the b minus 1 over e. And then once we have that, we know that this expression will go to 0, and then 0 minus 1 over e will be negative 1 over e. Okay, well, skipping part B here, look at part C. This requires partial fractions. We have integral of 2 dx over x squared plus 4x plus 3. If we can split this up into individual fractions, it'll be easier to evaluate. So if I factor the denominator, I get x plus 3 times x plus 1. If I split them up, I can go through the cover-up method. So the factor here is negative 3. So if I plug negative 3 into this expression, I'll get negative 1/2. So that will be my a value. And if I plug negative 1 into this expression, then I'll get 1/2. Okay. And so here we have something that's a little bit easier to work with. And sorry, I factored out a 2, so if I distribute that 2 through again, it'll become negative 1 and 1. And then if we evaluate this, we can go through use substitution, which will end up being a natural log rule. So this gives us, produces negative natural log of x plus 3. This produces natural log of x plus 1. We plug in the upper and lower bound being the b value, which represents infinity, and then followed by the 0. So b gets plugged in first. And then we plug in the 0. And if we clean this up, this will go to, this will just become let's see, natural log of x plus 1 over x plus 3. So once we have that, then notice that if we further evaluate this limit by plugging in our upper and lower bound, actually this doesn't help us at this point, sorry. We can, but if we're here at this point, it's a little bit easier to work with this if we can combine this to be one expression. So we'll use the quotient property and rewrite it as natural log of x plus 1. So this is actually a step that we're not able to get any further, make any further progress on. So we'll come back to this and work from this point here. Natural log of x plus 3 of x plus 1, plug in b. So if we plug in b infinity, this will just, the coefficients are the same. So as b approaches infinity, we know that this will go to just coefficient, which is 1. And if we plug in 0, we'll get negative natural log of 1/3. And then if we simplify this furthermore, it becomes negative natural log of 1 over 3. And we can write this as natural log of 3 as well. Okay, next video we'll continue from example 5 on.